Okay, so what we're seeing, what we're observing is that if we now take this body, right, it's in some configuration here, it's a current configuration. Whether we look at it in this basis or in that basis, okay, the position vector, right, of any point here changes as we have written in that last line on the slide. Okay, whether we take this basis, the original basis, or the barred basis, right? The relation between the position vectors in these two bases, right, is as we've written out here, right? In general, it's given as C plus QX, right, where C is a vector and Q belongs to SO3, all right? Now, that final form should look very familiar to us, because remember when we talked about rigid motions, involving a translation and a rotation, right, we had exactly this form, right? Okay, so recall that rigid body motions are of the form C function of time maybe plus Q also a function of time X. Okay? When we studied rigid motion, this is exactly what we did. Except back there, instead of X, little x, we had capital X because we were thinking of rigid motion starting from the reference configuration. What we are seeing now is that supposing we have the body in its current configuration, what we are seeing that when we talk about change of bases from this one to that one, okay, the change in the position vector of the spatial configuration is completely equivalent to just sitting in the original basis, not changing the basis, but taking the current configuration of the body and giving it a further rigid motion. All right? You see that? We just demonstrated that mathematically. Okay? So, let me state that. So, if x equals phi of x comma t is the current configuration, let me be even more specific. If x equals phi of x comma t is the current configuration, placement of a material point right? So the point that began at capital X is now at little x equals phi, okay? Comma, then x plus, which I'm going to now write as c, maybe it's a function of time, plus q, function of time, x is a rigid body motion on the current configuration Furthermore, by the development we just carried out in the last few minutes, we've demonstrated that this rigid body motion on the current configuration is completely equivalent physically and mathematically to change in bases, right? This is equivalent to a change in basis which is given by EI bar equals Q transpose EI. Okay? Essentially what we're saying is that, look, you hold the body. Now let's forget about, let's include the translation. You have the body in the current configuration. If you translate the basis and rotate it, okay, it is completely equivalent to keeping the same basis but going the other way with the translation and the rotation. Okay? That explains the appearance of Q transpose in the transformation of bases, but Q in the rigid body motion. Okay? So doing this is completely equivalent to doing this. Okay? Mathematically and physically. Okay. First, okay, so it's important to understand that. All right? What we've also shown here is that when we change the basis in this fashion, essentially what we've shown is that therefore the components of a vector ui, okay, in basis EI transform as UI plus, shall we say, equals Q I J U I. Okay? Under the change in basis. Okay? We were writing UI bar earlier, but I'm just using UI plus now instead of UI bar. Okay? Let me just write it here. Right? Instead of, I was using bar for components in the new basis. I'm just using plus now for components in the new basis, because this is what we're going to follow when we're thinking of it as rigid motions, right? When we're thinking of the equivalence of rigid motions to change in basis, I'm just using pluses for components after the rigid motion has been applied to the current configuration. Okay, just a change in notation. That's all. Nothing more than that. Okay. All right. All right. What about tensors? Okay. How do tensors transform? Same thing, right? Think of this. Let's suppose we have a tensor sigma, right? In the original basis, it is sigma ij ei tensor ej. Okay? Right? So I'm now going to do a change in bases. I have sigma ij. Ei we know is Q ei bar. Okay? That's fine. Okay? Tensor. Okay. In order to be consistent now with everything, let me also call this EI plus, right? So what we're saying now is EI plus equals Q EI, Q transpose EI. Okay, we've gone away from bar, from the basis EI to, instead of having the basis EI transform to EI bar, we're now saying the basis EI transforms to EI plus. Okay, just to be consistent with this plus notation, that's all. Okay, so for EJ now we have Q EJ plus. Okay, now taking the same approach that we had before, I'm going to write this as Q Ki EI plus tensor Q LJ EJ plus. Okay, using commutativity of everything, this is, I'm going to write this as Q Ki sigma ij, right, q lj, right, all of this ei plus tensor ej plus. Okay? But then just by observation, we know that these are what? Those are the components of our same tensor, right? The tensor is invariant, right? Sorry to whack my finger, but the tensor is invariant. What we have here are, let me see, wait a minute, I think right. Okay. Back here, I needed to have L. I needed to have Q K I E K plus and Q L J E L plus. Okay? And then when I come down here, I need to have likewise okay. So with those corrections, what we see now is properly what I've drawn a brace on is what we would call the sigma plus component in the new basis, right? So we see then that the transformation for the components is the following. Sigma plus is Q Ki sigma ij, where by sigma ij we mean the components of the tensor in the original basis, Q Lj. All right? Okay? All right. Now, having demonstrated this, what we can also write is this collection of components, right, in matrix vector form, right? What this implies is that now, remembering that sigma plus written in that form is the matrix of components in the new basis, we see that it is obtained by Q acting on the matrix of components in the original basis, Q transpose. Okay, so that's how tensors transform. Okay, and likewise, we can also say that Ui equals Q Ji Ui plus equals Qji Ui implies that the vector of components transforms as U plus equals Q U. Okay? All right. If this much is clear, one question. What happens with scalars under a change in basis, or alternately under a change in current configuration? So you have some scalar here, right? Think of the mass density. This is the current configuration. We have one basis, we go to another basis. What happens to the mass density? Alternately, we have this, we translate the body and rotate it the other way. Completely equivalent. What happens to the mass density, which is a scalar? Scalars do not transform, right? Or the transformation is the identity. Okay? So, scalars. Right? So, if we say rho of x comma t, right, equals rho plus of x plus comma t, right? You apply rigid motion, scalars don't change, mass density doesn't change. If you have the temperature, it doesn't change. Okay? It's only vectors and tensors that need to transform. Their components need to be written differently. Okay, so we'll stop here for this segment.